I'll get started with a little introduction of ourselves. So, Jess, sales director, do you want to say a few words about your background?
Hey, I'm Jess Tarrant. I graduated from Tarleton State University in Stephenville, Texas, and I've been doing sales in the oil field for a little over 14 years now. And I've been with Amplified Industries for 2.5 years, and I thought, looking at pump jacks all my life, that I knew everything there was to know just by looking at it about production. And as soon as I joined on with this group, I learned that I did not know a thing. And it's been a fun time seeing all the data that we're bringing in and what we can extrapolate to tell everybody else, that these guys that have been part of the field in pumping these wells, just to see how much data that we can give and change what your production and what your lease routes are looking like. But I'm director of sales, and I'm really proud of the team that we've got here.
Thanks. So my personal background, so I'm originally French. Came to the US for grad school, so I used to do quantum physics and aerospace. I was working with Siemens on big turbo machinery stuff. Did an internship with Schlumberger. I loved what I was doing. That kind of veered me into oil and gas. And that gave me a few ideas. So I did a PhD with them, then a few years of postdoc. I was in Boston at MIT, and decided to start my company really in 2020. We started in February 2020, which was a very good timing. And I'll present to you. So I've put a lot of slides together. Feel free to interrupt me and ask questions along the way. Kind of the angle around the presentation is I'll present a little bit the company, and then I want to show, everyone uses buzzwords like AI all the time, and what you're able to do with really high quality data and really high performance system, kind of what it really means on your average oil field. So kind of why we started the company is, the simple vision is that today industrial equipment is very expensive, very complicated to install, complicated to maintain, requires a certain niche skill set. And on the other hand, you have your phone in your pocket that is 1,000,000 times more powerful than any controller out there on your wells, and you've never had to read a 600-page manual to use an iPhone, and yet it can do a lot more, right? So there's, up until I would call it the 80s or maybe the 90s, industrial system were very sophisticated and the most high performance, and nowadays it's a little bit the opposite, where kind of consumer grade goods are more high tech than a lot of industrial grades equipment, in their capabilities at least. At the same time, there's a change of telecom, right? Most oil fields are connected with a SCADA system with antennas that look like this, and you have, to give you an idea, 100 kilobits per second. So that doesn't mean much, probably to some of you. It's about twice the dial-up speed of 1990s internet. And you compare that to, you have 5Gs everywhere, you have Starlink, you have 100 megabits per second. So you have a factor of, over 1,000 in speed that is now available at very affordable price pretty much everywhere in the continental US, and with Starlink just anywhere. We're just deploying our first Starlink system now. So this change happening at the same time. And then there's a couple, I would call it more political or society level changes. Just a lot more regulation in general coming for the oil and gas industry, EPA and whatnot. And then this plot is, I find it very interesting. It's a number of students who take petroleum engineering as a major over the years. And the idea is there's a lot of people that are going to be around my age and a lot of people around my dad's age, and very few in between. So there's kind of a generational shift that is happening today. So decided to start that company, and the idea behind the company was, how do you build a system that is extremely cutting edge? Thanks. How do you build a system that is very cutting edge, very powerful, to be able to fully automate whatever machinery you find on an oil field? So that means knowing what's happening at the surface on all your tank system, knowing what's happening on your wells, but also knowing what's happening deep on the ground in your wells, and using all that data to optimize it automatically and give insights to the engineers and to the operator. So practically speaking, what the system looks like is a set of hardware and a set of software. So the hardware are little devices, I didn't bring one today, but the size of a thick cell phone, basically. Little boxes, little bricks that you attach all over your machinery, and I'll show you in close-up what it looks like. And they will automatically talk to one another, they will automatically talk to the cloud using all kinds of Bluetooth and cellular network. The batteries will last over 10 years on all the equipment, so basically the life of the electronics. And we will record very high resolution. So what I mean by very high is, we record on the well, for example, your tubing, your casing, your position, your vibration, the current, the load. So all those channels at 50 to 100 points a second, and we just beam all that to the cloud. And the point of it is, today maybe we're only able to use, call it 5–10% of that data, but then we're able to constantly release new features, and I'll show you some of those in the following slides. So a little diagram, it looks like, we instrument the wellhead, we put our load cell, we've patented a design on the bridle, they're just very easy to clamp. We have a little gateway, typically in the electric panel, or with a little solar panel if it's a gas-powered well. Little devices on the tank battery, and then also on your injectors, on your pump, on whatever you want to tie into the system. And as the company grow, we've been building more and more capabilities. So we started, actually I started a company initially in northern Louisiana in the Shreveport area. The deal with the operator was, it's a water flood of very small, low production wells, says 700 wells, was we could do whatever we want as long as we don't break anything. And in exchange, they would get a discount when we have a product ready. So this is one of those wells, so very ancient, very, stuffing box isn't exactly tight. And so we started in this operator to instrument those kinds of oil wells. And as the company grew, now we're on many different sites. This is in Utah. This is a 14,000 feet well, kind of the other end of the spectrum. So from super small, very simple wells to very complicated. We're in the Permian on long horizontals. So kind of to show that we've designed a system also for business reason initially to go after smaller operators, smaller wells by production, typically strip a field, to really make sure we had something very rugged. And then we were leveraging all the data that we use to build a high quality system for the bigger wells, bigger operators out there. So when you talk about price of a system, there's a price of the software, price of the equipment, but typically the price of the install is a huge chunk of an actual system cost. So this is this next slide is a little video of Jess showing how to instrument a well. So this is fast forward, but just beat my record. That's 8 minutes to instrument a well. So what it means is that the cost to instrument a well is going to be, $200 basically for a full system that can do everything from the load, the current, the pressures, and vibration position, and so on. So now you have a system that is very rugged, very easy to deploy at scale, and there you go, it's running. So we spend a lot of time to build the hardware, and our hardware is manufactured in Maine, actually in the Northeast. We found a good deal with the factory that at the end of COVID, they were building all the temperature sensors you put in the vaccine box that needed to be refrigerated, and suddenly demand went to zero basically overnight. So we're able to make a good deal with them to build our stuff. So kind of the hardware part is the visible part that people see, but probably 75–80% of our engineering time is actually building what people don't see, so all the cloud infrastructure. To send that much data at a reasonable price point in a fast speed takes a lot of engineering on the cloud, so we use Amazon in our case, same thing with Microsoft Cloud. And so we send directly from our device to the cloud, to the user via software, or forward to whatever software they're using. And typical system today, you have your sensors connected to some type of field computer, some Rockwell or whatever PLC or pump-off controller that's communicated via your SCADA to another computer, and then you pay all kinds of software license and fees to manage all that. And you have a system that is very slow and is very expensive to maintain because there's a bunch of layers and it's been built over the years. So by starting from blank sheet of paper, you're able to have something very cost-effective and very, very fast, just more straightforward. And once all that data is on the cloud is really where we can show what we can do. We constantly release new features. The idea is to build all kinds of mathematical and physical model that will be able to ingest signals from those wells to be able to calculate or to control them in some optimal way. So I'll show a couple example of those technologies, but it is relatively easy to build all those features once you have real-time, high-quality data on the cloud. It's really, you bring your physical expertise after to build those. So just company results. So overall, we've seen 8% production change, about 30% of operating or runtime of the well reduction, eliminating pretty much 100% of all the spills. Last year, that was over 1.3 million gallons of spills eliminated, and we're still a very small company. So I started company in 2020. We've deployed now, this number is already outdated, we're at 2,000 systems deployed in 10 states. So basically everything except California, and we don't do gas, so none of the Pennsylvania and so on states. And there's 20 of us. There's 22 employees, 1 accountant, 1 sales guy, and 20 engineers today. Surrounded, Jess. So I'll talk about a couple kind of technical things we're able to do, and kind of like trying to show off some of the most advanced features, and feel free to ask me questions if you have any. So the first one I want to talk about is what we call production allocation. The idea is that if you have the system on the lease, we monitor every well and we monitor the tank battery, and we analyze every single stroke of every well, so we know exactly the runtime. We analyze every single pump fillage at every stroke, and we measure the level in the tanks every minute. And we're able, without buying any flow meter, to effectively build a mathematical model of that lease that allows us to calculate the real-time both oil and water production of every single well. So in this example, you have 3 wells, and this is a runtime of those wells over 40 days, and it moves up and down based on gas, based on maintenance on that lease. And what we can calculate is curves that look like this. This is the real-time oil, in this case, barrels of oil per day production of every of those wells. We can do the same thing with water. So if you have a couple wells on one lease, you can effectively complement or replace testing those wells or not have to buy very expensive Coriolis meters, for example, just by sending all that data from the wells and from the tank batteries and building models. And the same data can be used effectively to analyze your pump efficiency over time. As your well wear out, it affects how you calculate their flow. So when we started, this is not a feature we thought about, to be honest, but we just realized that we could kind of build this new model and roll out this new feature and see how it works on all the wells that we had instrumented. So that's one example. The second one is, so I was last week or the week before, I forget, in Midland at the Permian Basin Forum, and I presented a new feature. So this is more for the typically horizontal wells. So wells are going to have a variable frequency drive, so typically newer wells, higher production wells. And what I'm going to show here is the idea is that by using the VFD to its full potential, you're able to literally get the best of everything. You can have more production, less wear, and less power consumption from your wells. And you can do all that with pretty much just math and very little, no hardware. We connect our little device to the existing hardware, but the operator already spent tens of thousands on the VFD system. So to go a little bit into detail, so today the way people use those drives is typically two ways. Either if you have a long stroke unit, the VFD will slow down at the top and at the bottom to not explode the mechanism, basically, to be nice to the machinery, and it'll go fast in between. Or on a kind of normal conventional pumping unit, you will program your variable frequency drive to basically slow down if there's gas. So you'll have a little, in this case, Lofkin, a little screen, and you say if pump fillage goes below whatever percent, go from 6 strokes per minute to 3. And then when it's full again, you accelerate. So that's pretty much how everyone uses drives today. The way people change the speed of a pumping unit within each stroke today is actually by with different design of pumping unit. So on a conventional one, so your shaft does 360 degrees for one stroke, and you spend 165 on the upstroke and 195 on the downstroke. So it's basically spending more time on the downstroke to be nicer to the pump if you have gas issue. So just the slower it goes if you have gas, the less damaging it will be. But if you look at the Mark II units, it's the opposite. They go fast on the upstroke, slow on the upstroke, and fast on the downstroke. And that's for basically better wear and tear mechanically on the unit and smaller motors. So today, there's kind of those two designs that effectively change the speed of a pumping unit within the stroke. What you have is if you take a random well, so the example I'm showing here on wells are about 7,000 feet deep, so not crazy deep, but pretty average. And you go from 3 to 6 strokes per minute. 3 strokes per minute is the orange, 6 is the blue one. And as you accelerate, you have much higher loads. Both on the upstroke is higher and your downstroke is lower. And you see you have fewer oscillations. So if you accelerate well, you have more wear and tear, and your rod string is going to snap if you accelerate too hard. So there's a trade-off. And without going into the details, but just to show, the point of this plot is this is load on the upstroke, and this is load on the downstroke, normalized. And if you change the load by, let's say, 10% lower on the upstroke and 10% lower on your downstroke, you will go from 5 to 20 million cycle life of your wells. So just changing the strokes by 10% changes the life of your rod string by a factor of 4 or 5. So a small change of load has a huge change in your operating costs at the end of the day. So you have a little bit of a dilemma, right? If you have bigger wells, you can buy very expensive pumping units that will have long life and high production. You can buy a cheaper pumping unit that will have and run it slowly, so low production, low wear, but it's affordable. Or you can have a cheaper pumping unit that you're running at full speed, but then it's going to break all the time. So this trade-off in your equipment on a lot of those higher production well. And what we show here is you can basically get away from this dilemma, and you can buy a cheap pumping unit that you run fast and that doesn't wear very quickly. So to do that, what we do is, so we beam all the data from the load and the position and the RPM and so on, and the amps and the volts and all the VFD parameters in real time to our cloud. And we effectively identify a lot of parameters on the well, the inertia and things like this. And we send back controls of what RPM the motor should spin at multiple times a second. So within each strokes, the motor is accelerating and slowing down at points that we calculated. And on the right, this is, for example, the black curve is the speed of the motor in hertz. Negative just means it's downstroke. We just show positive in upstroke and negative in downstroke. So point is moving all the time. And what you end up having is, in this case, for the same stroke per minute, so this is a well that was running at around 5 strokes per minute, your loads now are much lower. You get the orange curve instead of the blue one. And so you see it's much smoother. So I call it noise canceling. It's the same thing, your Bose headphones cancel out external sound. It's the same thing here, you cancel out the stress waves that are coming from your pump to the surface by kind of moving the wellhead in the right way. And it doesn't cost anything because there's already the drive which does the heavy lifting, so just by programming it correctly. And this is just one example. We can actually do better. We're just starting to work on this point. An interesting application is for all those horizontal wells is you have a lot of, I'll come back to it later, gas slug issue, basically chunks of gas that today you program your controller to slow down when there's a bunch of gas. And what we can actually do is during the downstroke, so this is the speed of the pump, we'll slow down the well at one specific point here. We do the blue curve as compared to the orange, which was the default, and then we accelerate even more later. So if you expect you have gas around this point, we can now slow down so that the gas won't damage the pump, and then re-accelerate later so you can pump through the slug much faster. So overall, that's the R&D we're doing right now. You get higher production with less wear and tear. And those are kind of two examples, but you can optimize the VFD around a little bit of whatever you want. You could reduce the kilowatt hours you're using. You could optimize only for wear and tear. You can do the opposite. You can increase wear and tear to have even more production if you want. So kind of the idea is if you have your mass spring, you whip it at the end, so your pump will like shoot up a little bit, you get more amplitude, but the trade-off is you'll get more stress. So you can do really whatever based on your preference and the design of the machinery just by controlling the VFD. So a second example I wanted to go through. Another one, so to talk about the different kinds of wells that we see. So by analyzing stroke by stroke data, we're able to see how wells, if they can pump off, how they pump off. And based on that, how you should control them. So kind of most wells, you have your casing, it's full of liquid, you pump, 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 and then suddenly your pump fillage drops to, in this case, 40%. There's no more liquid. So in this case, it's after 350 seconds. So there's a small stripper wells after, after a few minutes, it's already pumped off, after 5 minutes. And in this case, it's kind of obvious you want the well to stop somewhere here, right? And there's no point in going further. But the reality is, on a lot of wells, it doesn't look like this. I mean, probably 20% of the wells we're on look like this. There's a lot that start to look like this. They have liquid, but they also have foamy stuff in there. And so the pump first starts, it's empty, then it's full, full, full. Then you pump through the foamy thing, and then it pumps off. So in this case, you want to stop the well here. And so the system will automatically identify this kind of change of slope and set the wells to run here, even if that moves over time. But then you have other wells that are even less clear, and you don't have a clean pump off. It just starts full, and it'll slowly go down. Basically, the whole thing is foamy. And then it becomes a trade-off of wear and tear versus production. And then you can identify. So this is, by the way, all data from real wells. This is a wells that's doing cycle. This one is a 1,500 second cycle every hours, and just has 24 of those curves superposed for one day. So you see those day after day, and then you can after make a calculated trade-off. Now I want to run the well up until here, because after it's going to cost too much in rod string repair, for example, and the extra production is marginal. So to give you an idea, so this is West Texas stuff. Some of those village looks like this, and the system will actually shut the well down much sooner because it identified that, hey, you only need to run half the time, and all this extra runtime wasn't giving extra production. It was very marginal. So you have half the runtime without any impact to your production in this case. So there's kind of all kinds of shapes possible basically on the wells, and what we've seen is even standard vertical run-of-the-mill wells have weird behavior, and I'm not even talking about the horizontal wells here that get more exotic. In this other case, what we saw was the opposite. If you wanted more production, it was worth going further down that fillage curve, but then there was a clear trade-off of the wear and tear on the well. So in this case, it's a calculation: what's the price of oil, what's the price of pulling a well, and then you can determine where you should be on that line. And then just for fun, in some cases it just looks like this, and it's just completely random. So this is more typically horizontal wells that bubbles of gas that will randomly, slug of gas that will randomly come through, and then that's when you really need a variable frequency drive for those cases. So to talk about those horizontal wells, right? So it looks like this. You have horizontal wells, and because the horizontal leg isn't perfectly straight, it follows whatever geology and based on whatever the driller did. Your liquid and your gas can separate into slug flows. You have chunks of liquid followed by chunks of gas instead of nice layers. And what it means is that the pump doesn't like gas, right? It likes to run as much as possible in pure liquid. Is that your pump fillage over time starts to look like this. This is 5 days of data, and your pump fillage goes full to empty, full to empty. So your average fillage wasn't too bad. It was almost 80%, like 75 something, which this is the data you would see from most normal system. It's fine. But in reality, it's an average of very good and very bad strokes. So in this case, we were able to build a machine learning system and train the well on this pattern. And this is 2 weeks of data on that same well. And initially, you see those slug. It was going from full to empty all the time. Then it kind of slows down. And at the end, so this is best case scenario, there was no more slug. In this case, with 30% less strokes. But most of the time, there's at least a lot less slug. So a lot less wear and tear on the equipment. And again, all of that you're only able to see because you're beaming everything that's going on with the given well. And the last kind of example before concluding that I want to show, this is just for fun, and I know you won't be able to read on this slide, but what we're starting to incorporate is, probably all heard about large language model, ChatGPT and all those things. We're feeding to those systems the data that we collect, the very high resolution. So in this case, we're feeding the max and min load over time. We're feeding every single surface and downhole card. We're feeding the raw load signal. And then you can train those large language model on petroleum engineering, basically on production engineering. And what we ask the system here is, hey, this is a raw data. What do you think? And I won't read the whole thing, but the quick answer is, this appears to be rod string failures, a drop in load. The surface card showed that it was normal, and then it dropped. The load cell signal peak amplitude dropped. Like it answered everything without us having to teach it that, just because those systems scrape the internet and have read basically every petroleum engineering book that exists out there. And so you can start to just feed all those raw signals directly to those systems to be able to automatically analyze and detect everything. And this is very funny. Like this took us 2 hours to set up, and it was very impressive. So we're working on building a lot of the math and physics to have the control system that we need. But for all of the analysis, then you can complement it with those language models trained on raw data that is sent by the machinery. So that's kind of the last example. To keep it on time, so to summarize, the idea is there was a system that gives full visibility and with very high-tech features are baked inside that we constantly release. We wanted to make a system that is very financially makes sense, so very affordable system, and that can eliminate all the spills. And the key thing is we're making something future-proof. We're not selling an expensive box that you replace every 10 years. The hardware is very transparent, and then we just constantly roll out new updates with the system, so it's all done at the cloud, at the software level, and it's very easy to scale. So that's the end of my presentation. Quick QR code, or you can just find my contact anywhere on the web. Thank you. I'll take any questions.
What does the acronym SCADA?
So supervisory, control, and data now, whatever, acquisition, yeah. It means telecom for industrial facilities. It's before telecom was ubiquitous for consumers, a lot of industrial facilities like power plant and whatnot has SCADA. It's just how all those sensors send their data to some central server.
Okay. On the control box on the well, is it, in the case of a VFD or a controller, is it when the controller is starting to stop it in the VFD and sending a 4020 to speed up so that?
Yeah, it's digital, it's Modbus, but yeah, same thing. Yeah.
And most of the card data and all that's done SCADA.
So through our telecom. So we have our system in case a well doesn't have a controller, and then we put our sensors and stuff. But if a well has a system, we'll just pull all the data digitally from the system in there, and it gets sent to our cloud. And then from our cloud, we can push it back to whatever user application and database.
So obviously this is all about rod pump and stuff, but like, is there stuff in the works for plungers and gas lift and ESPs and that stuff?
Yeah, so we started with rod pump because I didn't talk about my background, but my whole PhD was modeling rod pumps, which Schlumberger is like all the stress waves in the rod and then all the pressure waves in liquid and how they interact. So kind of started with rod pump, and also 90% of wells are rod pumps. So business-wise, it made sense. We're already tested, so we expanded on all the tank facilities, injection wells, flow meters, all kinds of machinery out there. We're releasing now ESPs, and we're sponsoring Texas Tech. They have several PhD students working with Professor Smith-Leggett on the gas lift. So we're sponsoring their research over there to add gas lift, and we're doing internal research on plunger lift. It's going to be all of them. It's just pump jacks first, then ESPs, then probably plungers will be ready, and then gas lift.
Will you hand the mic to Jess, because I haven't got to hear her speak.
Oh boy.
Really, what's the lowest, barrel per day, well site that you guys can really help out? I mean, truly.
So the
You
basically,
said stripper wells, I was just, at that point, I got curious, we have so many operators here in Oklahoma that, are mom and pop shops with a couple wells, and maybe,
yeah.
end of your business model, but.
Yeah, I mean, this is what they look like, our kind of worst wells, basically. So this was average production of 0.8. It's a water flood, so average, some wells produce more, some wells produce just water. Realistically, I would say, 2 barrels of oil, something like that a day. Like
2 to 3 barrels a day, like a.
yes, in that range, it starts to make sense. Or depending, if you can have wells that produce less, but that are spill all the time, or very remote, or kind of operating conditions are more exotic.
And it can also be like a hybrid of tanks on your field to monitor that part. If you're having some issues with tank monitoring, we can do tanks by themselves or just wells by themselves. It works together as a full ecosystem best, right? But this is, toppings for your burger. You just choose which parts you want, and we're going to control that part of the field, the highest resolution part that you have. So, with all the tanks that we have, we're getting the accuracy down to a fraction of the inch on the measurement with water, oil. We're working on the bilayer interface as well. So, there's a lot of new technology that we have that we're working on with our sensors that are, a lower price point, but still have feature rich.
And the tubing transmitter also does acoustics?
Yeah. But to be clear, it's probably not the kind of acoustics you're thinking of. Probably thinking of echometer shooting through level stuff. No, we like your pump makes sound that is transmitted through the tubing, and then we can use it. Originally, the company was called Acoustic Wells because we're doing that, and now we grew way beyond this, but yeah.
But it's still a big benefit.
Yeah.
Yeah.
So earlier you talked about a field like in Louisiana that have a whole bunch of wells and you can try to basically optimize it. So can you talk a little bit more about how, if you have 100 wells, they basically figure out which wells are actually making oil, which ones are making straight water, which ones are making anything. Because a lot of times when you're doing wide-scale testing, you're kind of just testing one well at a time, trying to figure out which well is producing, and you don't get that good data. So it sounds like, I think you can turn off wells, turn on wells, and kind of figure out which wells are actually producing.
Snapshot versus.
Yeah, what I showed, it's a little bit I think the production allocation you're referring to. So we don't even need to turn them on and off. We can, but basically we can tell what well is producing what. I mean, there's a limit, right? If you put 50 wells in one tank battery, it's not going to work. But if you put a couple, and I can't give you a hard number because it depends on how variable they are. The more they're variable, the more that they're running intermittently, the more they have gas, the better it is for the algorithm to figure out what each well is doing. And the more nothing happens, the harder it is for us. And then you have to do active turn on and off. And yeah, based on that so we use it for leak detection. We do all the alarms too. I didn't talk about that. But based on that, then you can, spend your time more wisely on the wells that deserve it.
So maybe you just kind of touched on it there, and I missed the part about the flow meters, but are you calculating three-phase flow based on your map, what you're telling me?
Two-phase, we don't do gas. Gas will just connect your gas meter if you have a total flow and pull that data. We will instrument your tank battery and we'll calculate oil and water flow rate for every well. So you'll get the same graph. This one was for oil, you'll get the same one for water for every well. And this is a couple points a day, so this is not every minute. We need a little bit of averaging, but it's a data point every, call it 6 hours, something like that.
But it's verified through tank readings?
Yeah, we have tank readings. So that's what the system does. It will match every well so that basically they add up to whatever happened at the tank level. And the reason we have to have a delay like those 5-6 hours is because you have a separator in between, which isn't instantaneous. Yeah.
And then kind of going back to the interface that you have on the wells, if you're just doing a bucket test out in the field, you're just getting a snapshot at that one time of what that well's doing. And if you take that to the bank off of this is what it's been doing for the rest of the time, it could be a good bucket test or it could be a bad bucket test. Whereas what we're providing on this is we're giving you full-time bucket tests without having to dump anything out or having that loss. So you have all this that's verified with high-resolution data.
I was talking to a friend this morning that they're dealing with what the fines over methane releases and tank battery stuff. You have sensors also that pick that up, that can shut the well down or stuff like that?
Yes and no. So first, to be very straightforward, we kind of put on hold a lot of our air quality stuff with the change of administration. It might not be the top priority for the next 4 years. What we can do is we can detect a lot of the open hatched that people forget, and then your tank will flash and release methane. We're not doing right now, so we've partnered with the company, we've done clear methane sensors that you can put on whatever site to automatically shut down. It's something that is technically easy for us to do, but I'm not convinced there's a good business case for us to do it. Yeah. So right now we do mostly the liquid spills, and then we'll detect some type of methane or VOCs emission. But we don't have to add a hatch sensor. The idea is you want to have as little hardware and as many conclusions as possible.
All right, any more questions? I'll take that.
Thank you.
Thank you.